Welcome to TypeScript Crash Course on Learn Awesome, your gateway to smarter, faster coding. So, what is TypeScript? In short, it's JavaScript with superpowers. JavaScript is powerful, but it won't warn you when your code's about to break. That's where TypeScript comes in. It catches errors before your app runs, helps you write cleaner, safer code, and makes complex projects easier to manage. In this crash course, you'll learn exactly how to set up TypeScript, work with types, functions, classes, and more, step by step. Let's get started. Before we dive into TypeScript itself, we need to ensure that your development environment is properly set up. That means Node.js and Visual Studio Code, the tools you'll be using throughout this course. First, let's make sure you have Node.js installed. Node.js is essential because it allows us to run JavaScript and TypeScript outside of the browser and gives us access to tools like NPM. To do that, go to the Node.js official website and download and install LTS or long-term support version, which is the most stable version. To verify the installation, open a terminal and run node-version followed by npm-version, and you should see version numbers for both Node.js and npm, confirming that Node.js is installed and ready to use. Now let's set up Visual Studio Code, also known as VS Code, our code editor for this course. VS Code is a powerful, lightweight editor with great TypeScript support and lots of extensions. Download and install Visual Studio Code from code.visualstudio.com. Visual Studio Code will make writing TypeScript much easier, providing you with real-time feedback and auto-completion as you type. Before we can start writing TypeScript, we need to install it. There are two main ways to install TypeScript, globally and locally. You can install TypeScript globally, which means you do the installation once and then it's available for all current and new projects on your machine. Though a good option to have for quick experiments, it's discouraged due to risks involved, primarily version conflicts. Therefore, we would not be using this method, but I'll just tell you that you can do this installation from command line using npm install-g TypeScript command, and then verify proper installation using tsc-version, where tsc stands for TypeScript compiler. Now let's have a look at local installation, which is the preferred method for most projects. By installing TypeScript locally, each project will have its own version, avoiding potential conflicts between projects that need different versions. But before we go too far in this rabbit hole, let me clarify a fundamental fact about TypeScript abundantly clear so that we understand what and why we are doing all of this setup. Neither browsers nor Node.js have any clue what TypeScript is. They just understand JavaScript. Whatever we do with TypeScript, like write code, configure, blah, 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 the end goal and result is that TypeScript files are compiled into JavaScript files. In other words, the end product of your project is not TypeScript, but JavaScript, which is consumed by Node.js, browsers, etc. All the steps we are about to do are steps in that direction. With that understood, the first step is to create a project folder. For that, choose a location on your machine where you would like to create your project, then follow my steps. We have now created a project folder which would host our TypeScript files and configuration. Let's proceed with TypeScript setup. So now from within your project directory, execute npm init-y and press enter. This converts your empty project into a node project by creating a package.json file in it, containing metadata about your projects like name, version, and a list of dependencies. Here's the file it created, and you can see there are no dependencies, so let's change that by installing our first dependency, that would be TypeScript. So for that, we are going to use the npm install command, where npm stands for Node Package Manager, which got installed with Node, and we're going to use the save dev flag to make it a development dependency, and then provide the package name, which is TypeScript. This will install TypeScript and save it as a dev dependency in your package.json. You'll also see a node modules folder and a package log JSON file, indicating TypeScript is now part of your project. In case you are unfamiliar, dependencies are external libraries which are downloaded during npm install step and made available in your project in Node Modules folder. To verify the installation, you can check the Node Modules bin folder and or run npx tsc version. If you see a proper version being spelled out, it means the installation was successful. Now that TypeScript is installed locally, you'll run it using npx, which is a command line tool to execute Node.js packages locally from within your project. It ensures you are always using the local version of TypeScript, even if there is a global installation of TypeScript on your machine. tsc is a command line tool that got installed with TypeScript and stands for TypeScript compiler. Now we can continue remaining steps from within the command prompt or shell, but a more fun way is to proceed from within Visual Studio Code, where we can see the result of each step as well. Since it's installed on your machine, from within your project folder, issue a command code space dot and press enter. This is going to start Visual Studio Code in context of your project. Let's open the integrated terminal from within Visual Studio Code and proceed with our setup. To do that, I am going to go to View menu and select Terminal. We can also start from here. I'm going to use command prompt and not PowerShell for now to keep things consistent with what we were doing. And you can see there is Node Modules folder where TypeScript has been downloaded and made available. All right, this is the package.json file, and it has TypeScript listed as a dev dependency now. Now that TypeScript is installed, we need to set up a TypeScript configuration for our project. This configuration file called tsconfig.json is crucial because it tells TypeScript how to behave, what files to include or exclude from compilation, and what compiler options to use. So let's create a tsconfig.json file, and to do that, we are going to issue a command npx tsc-init. This will create a tsconfig JSON file with a bunch of options, and this is the tsconfig file that it created, and we can look at the actual thing as well. And you can see that this is a tsconfig file which was created with a bunch of options, most of which are commented out. Only some settings are active, which were listed in the command prompt. You don't need to understand this file at this stage, except a quick word about some of these. First is the compiler options section. It is the most important section which tells TypeScript compiler trying to create JavaScript files from TypeScript files how to behave. Here we have a few important settings like target, which allows us to use modern JavaScript features and is a latest version of JavaScript, ECMAScript 2016, or in short, ES 2016. Then we have module, where we are using CommonJS. This is a standard module system used in Node.js projects and basically tells TypeScript how different files share code. That is, are they using export and require syntax or import export syntax in ECMAScript module, which is a newer way of sharing data. We are using a safer option CommonJS here. That's all I'm going to say at this stage and move on to the next options. The next option to consider is outdir. So Node by default, TypeScript would create a JS file alongside TS file after compilation, but it clutters your code with unintended files. So we use the outdir to tell TypeScript to save compiled files in a separate folder. I'm going to uncomment it and specify that folder name called dist. And now my compiled files are going to go to dist folder. Next, we have strict true, which enforces stricter type rules and helps you catch errors early and write safer code. This is an option that should always be kept true in your production code. So we are going to start this way. Two missing sections in this file are include and exclude. Note that by default, TypeScript would try to compile everything in your project. Adding include and exclude helps it focus on only the files that matter. That is your code, not the stuff from third-party libraries in Node modules, which is JavaScript anyway. So I'm going to add two sections, and these are arrays. So, all right, includes tells TypeScript to only look at files in your source folder. So let's create that source folder in the same breath. And this is where we are going to add our TypeScript files. And exclude tell it to ignore things like Node modules folder so that it does not try and find TypeScript files in there. So that's it, a clean and simple starting point. We'll update these settings later as your project grows. I did rush past target and modules as we can't get trapped in these details in a crash course. If you're not sure what terms like ECMAScript, ES6, or CommonJS mean yet, don't stress about it. They are safe defaults that work well for most beginner projects, and you will naturally learn what they mean as you build more with TypeScript. I try to add follow-up videos to explain these on my channel as well. For now, just know that these are different standards or specifications of JavaScript that have evolved over the years. With TypeScript installed and the configuration set up, we can now move to compiling our TypeScript code. Now to compile TypeScript code, you use the tsc command or TypeScript compiler command. If you have a tsconfig.json file in your project, simply run npx tsc. But doing so right now would result in an error because there are no TypeScript files in our project. So I'm going to save this tsconfig.json, go to click on source folder and create a file hello.ts. And in here, I'm going to write console.log TypeScript. Right? Now let's issue the npx tsc command. This command will look at tsconfig.json and compile all your TS files according to the settings defined there. By default, the compiled JavaScript files would be placed in the directory specified by the outdir option, which in our case is dist. Otherwise, they'll appear in the same folder as the original TypeScript files. So TSC was successful, and you can see there is a dist folder now with a file hello.js. And if we go there, it looks pretty much the same as the hello.ts, but trust me, that would look a lot different once we start writing proper TypeScript. So great, our TypeScript compilation was successful, but note as you start working with TypeScript, you'll want to automatically recompile your code whenever you make changes. This is where the dash dash watch option of TSC comes in. Instead of running TSC every time you change a file, you can tell TypeScript to watch your project for changes and compile files automatically. To do that, we run npx tsc with dash dash watch command. So as I run this, you notice that the command didn't finish, and now it's watching my code for changes and it's going to automatically compile. So now whenever I modify a TS file, TypeScript would immediately compile the corresponding TS file into JS without you having to manually retrigger the compilation. And that would be really fast. This is particularly useful when you're working on larger projects and need real-time feedback. So to test this, I'm going to change this hello to hi. Press Ctrl S to save. And now if I go to hello.js, you can see it is already compiled with my changes. And it also said file changes detected, starting incremental compilation over here. So perfect. Now you're set up with a TypeScript project that's ready to go. You've learned how to install TypeScript, configure your project, and compile your TypeScript files efficiently. In the next section, we'll dive deeper into TypeScript basics such as variables, functions, and types. We'll write TypeScript code, explore its features, and see how it improves our JavaScript development process. You'll also get hands-on with code samples, and by the end of the next section, you will be comfortable writing TypeScript code. Let's move on and start writing TypeScript. So welcome to the core TypeScript concept section and the crash course. Let's start by exploring the fundamental types in TypeScript. These include string, number, boolean, void, null, and undefined. These types are the building blocks of our TypeScript code. So let me type some examples and then I'll explain them. So in my source folder, I'm going to create a file variables.ts that I would be working with. Alright, so here in TypeScript file, we define variables using explicit types. For example, username is explicitly a string, user age is a number, and is logged in is a boolean, or true or false. This explicit definition helps to avoid runtime errors by ensuring values adhere to the defined type. The void type is usually used for functions that do not return a value. Null represents the intentional absence of a value, and undefined is for variables that haven't been assigned a value yet. The colon space type part after variable name is called type annotation. Notice how TypeScript uses type annotation to tell the compiler what kind of data we are working with. This ensures that when we use the variable later, the TypeScript compiler can catch any errors if we try to assign an incompatible type. So if I try to assign a string to user age, which is a number, I would automatically get an error, type string is not assignable to type number. Right, let me get rid of it. Okay, next let's talk about type inference. TypeScript is smart enough to automatically infer the types based on the values assigned to the variable, so you don't always have to specify the type explicitly. You see there is no error. In this case, TypeScript knows that the message is a string because we are assigning it a string value right off the bat. However, watch what happens if we try to assign a number to a message. And you see we immediately get a type error. Number is not assignable to type string. If I save, we also get the same error down below because our watch is running. So TypeScript will throw an error here because it inferred the type as string when we first assigned a string value. And now it sees that we are trying to assign a number which doesn't match with the type of the variable. That is true for other types like Boolean and also for types that have been explicitly defined as null or undefined. So if I try to assign not assigned with a value assignment, it would again complain that not assigned is undefined, so you cannot assign it anything. Let me get rid of these. So these were normal type annotations and assignments you would be working with most of the times. But sometimes you need more flexibility with types. Let's look at three special types: any, unknown, and never. So let me type first and then I'll explain. The any type allows you to assign any type of value to the variable. While this gives you complete flexibility, it also removes the safety that TypeScript typically provides, which can be risky and kind of defeats the entire purpose. So better not use it in any practical setting. Moving on. On the other hand, unknown is a safer option. You can assign any type to a variable of type unknown, but before using it, you must perform some kind of type checking. This makes it safer than any because it prevents error at runtime. So let me show you what I mean because it won't make any sense otherwise. So let's say I say console log strict value plus 1. Now we know it's a number, but we get an error strict value is of type unknown. So it's not letting us use this in console log. What this means that with unknown you still have flexibility. You can assign any type of value, but TypeScript won't let you use the variable until you check what it actually is. This forces you to write safer code. So let's try to use it after checking. So if I say if, see, it allowed me to use it this way. Let me get rid of this. I hope the difference between unknown and any is clear by now. Okay, our next special type is never. So let me type an example. Okay, the never type means a value that will never be returned. This function doesn't return anything, not even undefined, because it always throws an error and immediately stops the program. TypeScript uses never here to tell us you won't get a result from this function. All right, I think this is not a clear example, so let's come up with another. Let me type it first. Though ahead of its time in the course, and we'll get familiar with the syntax later, here we told TypeScript that status can only be success or error. This is called a union type, and pipe symbol means or. So our code is checking the status for its values like success or error and logging appropriate output in if and else if. But note the only possible options are being handled by if and else if clauses. The else clause at the end should never execute because status can only be success or error, which is guaranteed by the colon status type annotation. But just in case someone adds a new option later, like pending to the type, now you see there's a red squiggly appearing here. The never assignment will catch this thing. If TypeScript sees a value here that doesn't belong, it'll throw an error during development. Type pending is not assignable to type never. It is a helpful way to make sure we have handled all possible cases and nothing slips through. Alright, let's now talk about arrays and tuples. In TypeScript, we can define arrays with specific types, which ensures all elements in the array are of the same type. Here, numbers is explicitly typed as a number array, which means all elements in the array must be numbers. TypeScript will throw an error if we try to add something that isn't a number, which in this case it's doing on 7, which is a string. Next, discuss tuples. So tuples are similar to arrays but with a fixed length and specific type for each position. So let me type an example first. Here person is a tuple that expects the first element to be a string and the second to be a number. Trying to switch these types will result in a type error, like you're seeing right now. Alright, next thing is enums. So enums are a great way to define a set of named constants. By default, numeric enums are assigned numbers starting at 0 unless specified. Let me type first and then it would make sense. So in this example, direction.up is 1, direction.down is 2, and so on. This allows for more readable code, especially when working with values that can take on a limited set of possibilities. Enums can also be string-based, which might be useful when the values are meaningful strings rather than numbers. So let me type an example of that too. Here the enum values are strings, making it clear what each status represents. Let me also write a usage example so that we know what we are talking about, because enums are an extremely useful feature that you would be using when working with TypeScript. Enum status dot success, and the IntelliSense work as well, showing you the values. And we can do a console.log of current status, and this is going to output success in capital. And we can also see how to execute this file while the watch is running. So since everything is being compiled, we can say this slash variables.js, and you can see success being written out to the console as expected. This is useful when you want your code to be both readable and meaningful, especially when sending or receiving data in format like JSON. Alright, before this section ends, we have to talk about union and intersection types. So union types allow a variable to hold multiple types. You can combine different types using the pipe operator. You have already seen that example for the status, but let me type it anyway. Okay, here result can be either a string or a number. Both of these are allowed on line 56 and 57. But TypeScript will throw an error if we try to assign it any other type like Boolean, which is not allowed. Our final concept in this section would be intersection types. So intersection types allows you to combine multiple types into one. This can be useful when you need a variable to meet multiple type requirements. That won't make sense until I introduce it as an example. So here employee details is a combination of both person and employee. So employee must have both a name and an ID. This technique using this AND operator is called intersection types. So fantastic work so far. You have just covered TypeScript's core concepts from basic types to more advanced structures. Up next, we'll dive deeper into TypeScript's powerful features. So welcome to advanced features section of TypeScript, and in case you're wondering if what we saw in earlier section was any less advanced, well, you're right. We did venture into some advanced syntax, but there is no shortage. And if last section felt a bit rushed, that's because it was, as we have a lot of ground to cover. So let's get on with more advanced stuff. Let's start by diving into functions in TypeScript. Functions are a core part of programming, and TypeScript adds an extra layer of power to them by enforcing type safety. This means we can catch potential errors earlier, reducing bugs in our code. Every function in TypeScript has a function signature. The signature tells us what parameters the function expects and what type of value it will return. Defining function signatures helps ensure we use functions correctly and predictably. So let's come up with a simple example to illustrate how function signatures work. For this, I would be using a new file. I would call it advanced ts.ts and type first. Talk later. Right, in this example, the function greet has a signature that indicates it expects a string parameter called name, and it will return a string. This type checking is built in, so if we try to call this function with an argument that's not a string, TypeScript will alert us to the error. Let me show you how TypeScript enforces this type safety. Watch what happens when I pass the wrong type of argument to this function. Right, if I hover, it says argument of type number is not assignable to parameter of type string. Right, but this would go away if I convert it to a string, and now the error is gone. So as you can see, TypeScript catches the error before the code runs, which helps makes our code safer and more reliable. This feature is one of the reasons TypeScript is so useful. It provides feedback as we write our code. Now let's dive deeper into the parameter types. In TypeScript, we can specify the exact type of each parameter a function accepts. By doing so, we ensure that only the correct type of data can be passed to the function, which minimizes bugs. Just as we define parameter types, we can also specify the return type of a function. This tells TypeScript what type of value the function should return, helping ensure that the function's output is as expected. So let's update our greet function and change its return type, and you'll be able to see what happens if we are returning the wrong type. So I'm going to go ahead and change this string, which is the return type of this function, to number. And now you can see a red squiggly appearing under return. Type string is not assignable to type number. Why? Because the function is returning a string here, but its return type is now number. So it's giving us an error immediately. This level of enforcement helps us avoid unintended mistakes. This is a very small example where a function is just one line, but you can imagine in production code where you have function that is considerably large and can have multiple return statements. This type of enforcement would help us avoid unintended return values which the callers aren't expecting. Let's move on to optional and default parameters. These features give us more flexibility when writing functions. An optional parameters allows us to pass a value, but it's not required. To define an optional parameter in TypeScript, we add a question mark after the parameter name. Let's look at an example when we have an optional age parameter in the greet function. So I'm going to fix this return type back to string, and I'm going to introduce age question colon number. Okay, in this example, the age parameter is optional. You can call this function with or without providing an age value. TypeScript will handle both scenarios. Let's give it a try. And you can see the output, hello Alice, you are unknown years old. But if I change this to 30 and call again, hello Alice, you are 30 years old. So as you can see, TypeScript allows us to call this function without passing the age parameter. But your function gracefully handles this by assigning a default value, in this case unknown for the age. Next, look at default parameters. A default parameter is one that has a predefined value if no value is passed when the function is called. This ensures the function always has a value to work with, even if it is not provided by the caller. So let me introduce the change here. So let's say I provide a default value of 50, but to use that, I have to get rid of this optional thing because now it would always have a number. Let's see what happens. So first I'm going to go with this example, which is the same output, but if I remove this and call it again, hello Alice, you are 50 years old, using the default value. Now this is a dumb example, I know you would never be using this sort of logic to give a predefined age, but you can see the point. This makes our functions more flexible and prevents errors when values are missing. So far we have covered function signatures, parameter types, return types, and how to use optional and default parameters. These features are essential for writing type-safe functions in TypeScript, making it easier to catch errors early and ensuring our functions behave as expected. Now let's move on to function overloading. This is a powerful feature in TypeScript that allows us to define multiple function signatures for the same function, with each signature handling different numbers or types of arguments. So in TypeScript, we can define several different function signatures for the same function and then implement the function to handle each case. Let me show you an example of how function overloading works. But before we get into it, let's look at a regular function. Let's execute it and see the result if it's as expected. And yes, it is. This works fine. The function accepts either a string or a number and handles both cases inside a single implementation. But here's the issue. From the outside, there is no easy way to know what it actually does with each type. This is where function overloading can help. It lets us clearly define multiple expected usages for a function, each with its own input types and return behavior. Now we have defined two overload signatures, one for a string input and one for a number input, followed by a single shared implementation that handles both. A very important point to remember, only one implementation is allowed. All overloads must share the same function body. So what's the point? Well, let me show you how this helps when you are writing code in an editor called VS Code. Let's say you intend to use this format function in an API, which is going to be used by other developers in editors like VS Code. So let me just type first, and then the benefit would be clear. Now, when a developer calls the format function in VS Code, they'll see two separate options with helpful documentation. See here. This is for the first overload, which is giving you the format a string by trimming and capitalizing. And if I press the down button, it gives me documentation for the other overload. You would notice it's not even showing the actual implementation. It just tells you how it handles strings, and the other one tells you what happens when you pass in a number. This makes your code more readable, self-documenting, and easier to work with, especially in larger teams. I hope you were able to grasp the benefits of overloading. Let's now move on to some advanced function features that TypeScript offers. These features allow us to write more concise, flexible, and powerful functions. Arrow functions are a shorthand way of writing functions in JavaScript, and you may already be familiar with them, but in TypeScript they become even more useful, especially because of how they handle the this keyword. Now, those of you who watched my JavaScript crash course will remember how this behaved differently in regular versus arrow functions as we discussed this a lot. But for the rest of you, and including yourself, let me give you a quick recap because while this isn't a TypeScript specific feature, it becomes more important when working with TypeScript. In regular functions, this refers to the object that call the function. Arrow functions, on the other hand, do something different. They lexically bind this, which in English means they capture it from the surrounding context. So let me type an example and that would be clear then. Okay, let me get this out of the way. I meant the terminal, not this. Okay, so in the first example, we are using a regular function inside setTimeout. Here, this is no longer pointing to the person object. Instead, it is pointing to something else entirely. And TypeScript doesn't know what this is supposed to be. In fact, it gives us this warning. This implicitly has type any because it does not have a type annotation. This happens because in TypeScript, we are expected to be explicit about types, even for this. And fixing this in a regular function is not beginner friendly at all, so I wouldn't even attempt that. So why is this happening? I can quickly tell you that while greet function belongs to the normal person object, the set timeout callback function does not belong to that object. It belongs to something called global execution context, which calls it once the 1000 millisecond timeout occurs. Using this keyword in that callback means it does not point to the object, and if logged to console, we find out that it is undefined. While knowing that using that keyword is useless at runtime, TypeScript add another level of complexity. that it requires you to specify the type of this at compile time. At this stage of learning, it suffices to say that there is no easy way out except one, using arrow functions. See, arrow functions handle this differently. I already used the term lexically bound before, which means they can infer this from the context in which they are operating. In the second example, this indeed points to arrow person object, and we don't get any complaint from TypeScript either when we use this keyword in our second example. All it takes is removal of function keyword and putting an arrow before the function body. What more can you wish for? So even though arrow functions might just seem like a shortcut, in TypeScript they actually help you avoid confusing bugs and frustrating type errors related to this. And that's why we are covering them here. Arrow functions also allow us to write shorter, more concise functions, especially for one-liner functions. Instead of using the full function keyword, we can use a more compact syntax. Let me show you a simple example of how you can write a one-liner function using arrow functions. This is much shorter than a traditional function declaration, but it does exactly the same thing. The arrow function is ideal when you want to keep your code compact and easy to read. I can quickly demonstrate using a console log. So now if I do this, you can see 8 being written through the screen. All right, this brings us to the end of the functions part. In this part, we explored arrow functions and how they handle this lexically, as well as how they allow us to write concise one-line functions. Arrow functions are great for reducing boilerplate code while ensuring that this behaves in a predictable way. Let's move on to another powerful feature in TypeScript called generics. Generics allow you to write code that works with any type, while still keeping the benefits of type safety. Think of generics like fill in the blank type. You don't log in a specific type, instead, you write a function that can work with whatever type the caller provides. Making any sense? Of course not. So let me type an example and then it would. Alright, so in this particular example, t is a placeholder or a type variable. When we call the function, TypeScript figures out what t should be based on the value we pass in. Right, so as you can see, t became number in the first call and string in the second. You didn't have to write different functions for each. That's the power of generics. Most of the time, TypeScript can figure out the type for you, but sometimes it can't. In those cases, you can tell it explicitly using angle brackets. Alright, let's say you want to parse a JSON string here and treat the result as a specific type. You can pass that type in manually like this. Alright, we expect the output to be Alice. Let's see. And here we go. Alice got printed to the console. So what happened here? Here we explicitly told TypeScript the result of parsed JSON should be treated as a type user, which we defined right here using the type keyword. This gives you proper IntelliSense, type checking, and error detection. Super helpful. And this pattern becomes especially useful when you are working with the fetch API and getting data from a server. Since fetch gives you a raw JSON, using generics like this help you safely work with the expected shape of the data. In fact, I think I won't be doing any justice if I just use this dummy data example and ignore this super important and practical use case. So let's take one step further and go ahead with a real world use case because you would definitely be using this example that I'm about to show you. So JSON placeholder is a website that gives you dummy JSON objects when invoked using its API. So that makes it an invaluable asset when trying to show you a real world example using type fetch. So by passing post type to this fetch post function, we are saying I expect this API response to match the post structure. And this is a post structure, ID, title, and body. And because of that, boom, full intelligence, type safety, and helpful tooling. You notice that as I typed fetch post your title, I got this complete intelligence. And even when I hovered over this then, you can see the callback function had this value post being written out. This is how to get everything working smoothly in the typed world of TypeScript. And this brings us to the end of the generics section. In this section, we figured out that generics let you write flexible, reusable, and type-safe code. You can manually specify the type when TypeScript can't infer it, like with JSON parsing, and you can constrain generics using extents to require certain properties. It's the best of both worlds, flexibility and safety. Now let's dive into higher order functions. Higher order functions are functions that either take other functions as arguments or return functions. These are powerful concepts in functional programming and can make our code more abstract and flexible. By using higher order functions, you can pass behavior to functions, making them more versatile and reusable. Let's look at an example where a function returns another function. Need an aspirin? All right, hopefully not after I explain this. So in this example, we have a function called create multiplier that takes a factor and returns a new function. The return function multiplies its input by the factor we passed when we called create multiplier. Let me show you how this works in practice and hopefully it will make sense. We can create a multiplier function for any factor and then use it to multiply a number. Is it starting to make sense now? As you can see, we created two different multiplier functions, one that multiplies by 2 and another that multiplies by 3. By calling create multiplier with different factors, we create new specialized functions. This is a great example of how higher order functions can be used to generate custom behavior dynamically based on the parameters provided. If it's still not making much sense, note this is a type, which is representing a function which takes a number parameter and returns a number. So here we are creating that function and returning it as a return value of create multiplier. So when you call it with 2, we return a function which takes an n parameter and its body comprised of multiplying n by factor, which was 2. I can only hope that it made sense, but if it did and you are able to use it in practice, it would be an invaluable lesson that you will learn today. So we can move on and look at a higher order function that accepts another function as an argument. This is another form of higher order function and is commonly used in many programming scenarios. So in this case, we'll define a function that takes an array and a callback function. The callback will be executed for each element in the array. You're already familiar with how callback functions work, so hopefully that should be a bit simpler. So let me type the example. So here process array takes an array of numbers and a callback function. It then runs the callback function for each element in the array. Let's see how this works in action. So we'll pass a function to process array that multiplies each number in the array by 2. As you can see, process array accepts the callback and calls it for every element in the array, allowing us to perform a custom operation on each element. This is a very common pattern, especially when dealing with operations like filtering, mapping, or reducing data. So in this mind-bending section, we covered higher order functions. These are functions that either return other functions or accept functions as arguments. We saw how higher order functions can make our code more flexible and reusable by allowing us to pass behavior around. So to wrap up the entire section of functions, we have covered several key features of functions in TypeScript. Let's quickly review what we have learned. Function signatures, we learned how to define the parameters and return types of functions to make them type safe. We saw how to make parameters optional or set default values to make our functions more flexible. We explored how to define multiple function signatures for the same function to handle different types or numbers of arguments. In arrow functions, we discussed how arrow functions are concise and how they handle this lexically. We also just saw how to pass arrow functions as arguments to another functions or return arrow functions as return value from higher order functions. In generic section, we learned how to use generics to write flexible functions that can handle different type of data. And in higher order functions, we explored how functions can accept other functions or return functions, allowing us to create more abstract and reusable code. These concepts are some of the building blocks for writing powerful and flexible code in TypeScript. I encourage you to practice using these features in your own projects to become more comfortable with them. The more you practice, the more confident you will become in writing type-safe and maintainable code. In the next section, we'll talk about object-oriented programming with TypeScript. Stay tuned. So, welcome to the object-oriented programming with TypeScript sections. One of the core features of TypeScript is that it supports classes and interfaces. This gives us a great way to organize and structure our code. In TypeScript, we define classes just like we do in JavaScript, but with additional features like typing. A class is essentially a blueprint for creating objects. Let's go ahead and create a class. So I'm going to create a classes.ts and create a class called person. All right, we are getting some red squiggly underneath, and if I hover over, it says duplicate identifier person, and variables.ts also has a person variable defined. So even though our tsconfig.json says we are using modules like module common.js, TypeScript doesn't fully treat our files as separate modules unless we explicitly use import or export. So neither variable.ts or classes.ts used export or import, so TypeScript assumes they are part of the same global scope, and it gets confused and hence throwing this duplicate error. The fix is easy. We just need to tell TypeScript that this file is a module by prefixing this class with export syntax. Now TypeScript knows person only lives in person.ts, and if I want to use it elsewhere, I'll have to import it. So no more naming conflict. All right, that got rid of the issue on person. What is going on here? Property name has no initializer and is definitely not assigned in the constructor. So we haven't reached the constructor part yet. Here TypeScript is being super cautious. It wants to make sure that all class properties will have a value by the time the object is created. Since I didn't give name a value right away and I didn't assign it in a constructor, TypeScript assumed it might be undefined. And that breaks the strict property initialization rule being introduced because of the strict mode in tsconfig, but that would go away by the time I reach the constructor stage. So let me write the complete implementation and then we'll see. Right, we are done. And in this example, the class person has two properties, name and age, and a method greet that returns a string. The constructor method is used to initialize the object when it is created. Constructor method is a special function within a class. It runs when an instance of the class is created. Here's how we can create a new instance of the person class. So outside the person class definition itself, I'm going to say const person1 equal to new person Alice and 30 and console.log. So when we create a new object, we pass in the values for name and age. The greet method then uses those values to output a greeting. When we do new person, it would automatically call this constructor function and pass in those arguments. So as you can see in this example, classes in TypeScript can have both methods and properties. Methods are functions that belong to a class, and properties are variables that store data for each instance of the class. Just like how a person has a name and an age, each instance of the person class has its own name and age property, which are unique to that instance. The method greet allows the object to behave in a certain way. Now let's talk about inheritance. Inheritance is one of the pillars of object-oriented programming, and it allows one class to inherit the properties and method of another class. So here we have created an employee class that extends the person class. One second. The employee class inherits all the properties and methods from person. We also added a new property job title and a greet method that extends the functionality of greet method of person class. Think of it this way. A person is like a general blueprint for any person, but an employee is a special type of person with the additional property of job title. So an employee inherits all the basic properties of a person, but adds something new specific to them. So here, once the constructor of employee is called, it first calls the constructor of its parent, that is the person class, with name and age, since it only takes two parameters. And then it assigns the job title parameter to its job title property. In greet function, it is returning super.greet, which is going to return, hello, my name is this and I am this years old, and it's suffixing it with I work as a job title. So let me quickly try it out. Right, let's give it a go. Something went wrong. Oh, I forgot the parenthesis. All right, here it goes. Hello, my name is Joe. I am 40 years old. I work as a supervisor. Perfect. All right, next we'll discuss interfaces. An interface in TypeScript is like a contract. It defines the structure of an object, including what properties and methods an object should have. Let's create a simple interface. This interface defines the shape of an object that has a name property and a greet method. Any class that implements this interface will need to provide these properties and methods. To implement an interface, we use the implements keyword. Let's implement the greetable interface in a class. Cut this to put it in its logical place. And I'm going to make the class person implement this. Here we go. We made the person class implement the greetable interface, so it must have a name property and a greet method. By implementing an interface, we ensure that our class follows the structure defined by an interface. If we try to add or remove a required property or method, TypeScript will give us an error. For example, if we remove the greet method from person, TypeScript will throw an error because person no longer satisfies the greetable interface. Let's see. So I comment this out and we are getting this error. Class person incorrectly implements interface greetable. Property greet is missing in type person but required in type greetable. See? Okay, gotta bring it back. So interestingly, interfaces can extend other interfaces, just like classes can inherit from other classes. So let's extend the greetable interface to create a new interface, employee greetable. I'm going to say, all right, here employee greetable extends greetable, adding the job title property. So if I copy this and make the employee class implement employee greetable, now the employee class implements employee greetable and extends person, ensuring that it has both name, job title, and the greet method. Now let's move on to some advanced object-oriented programming concepts in TypeScript, starting with abstract classes. So abstract classes are classes that cannot be instantiated directly. They are meant to be extended by other classes. An abstract class can contain abstract methods which don't have any implementation but must be implemented by its subclasses. So in this example, the animal class is abstract, meaning you cannot create an instance of animal directly. It has an abstract method make sound that is implemented in the dog class. The move method is implemented in the animal class and is available to all subclasses. And no, I don't know what does a fox say, so I'll stick with the dog's example only. Right, so the abstract methods in an abstract class defined using the abstract keyword are like promises that subclass must fulfill. They define a contract but leave the implementation up to the subclasses. As mentioned earlier, you cannot instantiate an abstract class directly. This would give us an error. So if I try to do const animal equal to new animal, you see there's an error. Cannot create an instance of abstract class. That wraps up our discussion of abstract classes. Next are visibility modifiers. So visibility modifiers in TypeScript are used to control the visibility of properties and methods in a class. These modifiers are public, private, and protected. Think of public as something you are allowed to see and interact with, like an employee's name tag. Private is something you can't see, like their salary. And protected is a middle ground, something that can be seen within the class or its subclasses, but not outside of them. Let's take a look at an example. So in this example, the name property is public, so it can be accessed anywhere. The age property is private, so it can only be accessed inside the class. And the job title is protected, so it can be accessed inside the class and in any subclass. So let me show you with an example. As you can see over here, we can only access the name correctly. We cannot access a person's age or, or its job title. So to get the person's age, we can use this getAge function, which has access to the age property, and this is the preferred method for doing such operations. Job title would only be accessible to the methods of protected person or any class that extends protected person. I hope that part is clear. All right, finally, we can move on to static members. So static members are special because they belong to the class itself rather than instances of the class. They're useful when you want to share functionality or data among all instances of the class. So let's look at a static method. Right, so in this example, the add method has the static prefix. So you can call it on the class itself, not on an instance. So let me show you how. So as you can see, we did not create any instance of the math utility using new math utility operation. We are calling the add method on the math utility directly. And this is going to output 8 to the console. This, you can see 8 being logged to the console. Static properties work the same way. They belong to the class, not to any instance. The most popular example for that is a counter. So let me show you. So here we are using a static property count that keeps track of a value shared by all instances of the counter class. So anytime I use counter.increment, the count variable would be incremented and you will see its value over here. So if I do this, you can see 1, but if I copy and paste it 2 times, then you're going to see 2 being logged to the screen. Right? So today we covered a lot of important concepts in TypeScript's object-oriented programming model, including classes, interfaces, inheritance, abstract classes, visibility modifiers, and static members. These concepts are the building blocks of writing clean, maintainable, and scalable applications using TypeScript. By the time you have seen that there's so much content to cover in this crash course that we are having to rush past every concept. So I hope you are understanding everything. But if you're not, let me know in the comments and I'll try to help you out as quickly as I can. All right, everyone, moving on to the advanced TypeScript features section. In this section, we are diving into some of TypeScript's advanced features that will make your code more powerful, reusable, and type safe. We'll start by talking about literal types, which is a powerful feature TypeScript offers for restricting values to specific fixed types. Then we'll move on to more advanced topics like type guards, type assertions, keyof, and indexed access types, and conditional types. These concepts will help you ensure your code behaves exactly how you intend it to. So let's begin with literal types. In TypeScript, a literal type allows you to specify a specific value for a variable rather than a broad type like string or number. Literal types are useful when you want to limit a variable to a small set of predefined values. For instance, imagine you are working on a function where you need to restrict the possible input to a set of values like red, blue, or green. Instead of just using string, you can define it as a string literal type to enforce that only those values are allowed. So let's go to the example. In this case, the color variable is restricted to only three valid strings, red, blue, and green. If you try to assign yellow, TypeScript will give an error because that's not part of the allowed literal set. This ensures data integrity by preventing invalid values from being assigned to variables or passed as function arguments. Literal types are not just restricted to strings, they can work with numbers as well. So let me give you a quick example. In this example, the variable dice roll can only have one of the values 1, 2, 3, 4, 5, or 6. Any other number like 7, 15, etc. will result in an error. Numeric literal types are particularly useful when you are dealing with a set of possible numbers like dice rolls, ratings, or age categories. They make your code more predictable and safe. We'll now move on to type cards and explore how you can narrow down types dynamically to enhance the flexibility of your TypeScript code. Right, so in TypeScript, type cards are techniques that help you narrow down the type of a variable within a specific block of code. They allow you to perform checks and tell TypeScript the exact type of a variable, ensuring type safety. Let's start with two commonly used built-in type cards, typeof and instance of. These are used to check the types of variables during runtime. For example, if you want to check whether a value is a string or a number, you can use typeof. Here's the example. In this code, we use typeof to check if the value is a string or a number. If it's a string, we return its length directly. If it's a number, we convert it to a string and then get its length. Similarly, we use instance of to check if an object is an instance of a specific class. Here's an example. In this example, we use instance of to check if the parameter person is an instance of the person class. If it is, we access the name property, otherwise we treat it as a string. Now let's talk about custom type cards. Sometimes you might need to create your own type cards. These are functions that return a Boolean value and help narrow down types in a more specific manner. For example, let's say we want to check if an object is a person type. We can write a custom type card like this. Here is person is a custom type card. The return type value is person tells TypeScript that if isPerson returns true, the value is definitely of type person. Let's see how we can use this custom value type card in a function. In this example, the isPerson function narrows down the type of person so we can safely access the name property if it's a person. And you can check that if I click over here and press dot, you can say it's giving me the name property just like it would if it knew that the person is of type person with a capital P, not any. If any of this didn't make sense, let me know in the comments and I'll try to explain further. A related concept to value is person, which results in a type being determined, is type assertions, which is our next topic. So type assertions are a way of telling the compiler, trust me, I know the type of this variable better than you do. It's useful when you are certain about the type of a value, but TypeScript isn't able to infer it automatically. So there are two ways to perform type assertions in TypeScript. Let's take a look at both. In this example, some value is of type unknown, which means we don't know the exact type. However, we assert that this is a string using asString and then access its length property. Alternatively, you can use the type syntax in angle brackets, which looks like this. This syntax works in the same way as asString, but it's a little more common in JavaScript projects. Both methods achieve the same result. The important point is that type assertions do not change the runtime behavior of the code. They just tell TypeScript to treat the value as a specific type. Now let's dive into keyof and indexed access types in TypeScript. These are powerful features that help you work with object types and their properties more effectively. So first, let's talk about the keyof operator. The keyof operator takes an object type and produces a union of its keys. This is helpful when you need to refer to the keys of an object type. For example, let's say we have an interface representing a person. We can use the keyof operator to get the keys of the person interface as a type. In this particular case, person keys will be a union of the string literal types name, age, and address, which are the keys of the person interface. Let's see a practical example of how this can be useful. If we want to create a function that accepts a key from the person object, we can use keyof. Here the function getValue takes a person object and a key of the type keyOfPerson. The key can only be one of the keys from the person interface, ensuring type safety. Here we go. We were able to access the address of the person using the address being passed as a keyof. Next, we are going to explore indexed access types. Indexed access types allow you to look up a specific type in an object or array based on a key. This is done using square brackets and the key you want to access. Let's take the same person interface. If we want to access the type of a specific property dynamically, we can use indexed access like this. In this example, person square bracket name gives us the type of the name property, which is string. Indexed access types can be useful when you want to dynamically extract types from objects or arrays based on keys. Right, now let's explore conditional types in TypeScript. So conditional types allow you to express logic about types, where the type changes based on a condition. Think of them as if-else statement for types. Let's start with basic conditional types. A basic conditional type has the following syntax. And this reads as if type T extends type U, then the type is X, otherwise the type is Y. It won't make sense without an example, so let's write an example to make it clear. Suppose we want to create a function that checks if a value is string, and based on that we return either a string or a number. Here's how we can use a conditional type for that. Here isString is a type that gives us yes if the input type is a string and no otherwise. This is super useful for creating type helpers or building logic into your types without writing any. That finally brings us to the end of advanced TypeScript topics. In the next section, we are going to look at some practical TypeScript topics, so stay tuned. So great, let's move forward with practical TypeScript topics section. So now let's dive into asynchronous programming in TypeScript. Asynchronous programming is crucial for handling tasks like reading from a file, making HTTP requests, or querying a database without blocking rest of your program from running. TypeScript makes it easy to work with asynchronous code and adds type safety along the way. First, let's look at typing promises. A promise is a placeholder for a value that will eventually be available but isn't yet. In TypeScript, we can type promises to ensure that the value the promise resolves to is the right type. For example, when you use a promise to fetch data from an API, you want to ensure that you get back a specific type of data. Let's take a look at how to type a promise that resolves with the user object. In this example, the getUser function returns a promise of type user. This means TypeScript knows that the promise will resolve to a user object which has an ID and a name. You could also handle errors, ensuring that your code is robust and that the type system helps prevent mistakes. Next, let's discuss async iterators. An async iterator is a way to iterate over asynchronous data one piece at a time, like reading a file line by line, fetching pages of a result from an API, or processing data as it streams in. You can use an async generator function to create an async iterator. Here's an example of an async generator that fetches data in chunks. In this example, fetch data in chunks is an async generator that fetches data page by page from an API. Every time we call yield data, it gives us the next chunk of data, and the for await of loop can be used to consume those chunks. Let's see how we can use this async generator in action with a for await of loop, which allows us to iterate over this asynchronous data. Here, the for await of loop will iterate over each chunk of data as it becomes available, and we can process it immediately. Type must have this method. The problem is async iterators are a very new concept relatively in TypeScript. The target that we have set in our tsconfig.json does not support it, so we need to change it to 2018 or higher, ECMAScript 2018 or higher. So let me select this and see if the error goes away. And yes, it does. Perfect. Right, moving on. One of the great things about TypeScript is that it can be integrated with third-party JavaScript libraries, and with TypeScript, you even get type checking for those libraries. To make this possible, we use type definitions. Type definitions describe the structure of a library's API and provide type information so that TypeScript knows what functions exist, what arguments they take, and what they return. The most common source of type definitions is the DefinitelyTyped project, an open source community effort where developers contribute type information for popular libraries that weren't written in TypeScript. Type definitions from DefinitelyTyped are published as npm packages under the @type scope. So when you install something like @type/lodash, you're getting those community provided types, which TypeScript can pick up. Let me show you how. So here I'm installing Lodash library, which is a purely JavaScript library, but its type definitions are published under the @type/lodash to npm. So we can install those type definitions like this npm install save dev. Here @type/lodash is the type definition package for Lodash. After installing it, TypeScript will recognize the types of Lodash functions, giving you IntelliSense and catching mistakes like passing the wrong argument types. If you ever need to check whether types for a particular library exist, you can always go to npmjs.com, which is the main repository for most of the npm packages you install from using npm install command, and search for @type/library name, and you would find type definitions for most of the popular libraries here. Right, let's now look at one of the most real problems you'll hit when working with TypeScript. That is what happens when you want to use a JavaScript library that has no TypeScript types. So remember, TypeScript doesn't automatically know JavaScript libraries. If a library is written in TypeScript, awesome, no problem. But if not, TypeScript looks at it and says, a cool library, but I have no idea what functions or types are inside that thing, so I can't use it. That's where type definition files step in. Type definition files are files with .d.ts extension. They are like cheat sheets that tell TypeScript, here's what's inside that JavaScript library and what are the types of functions, variables, and classes being used in it. And normally we would just install types from DefinitelyTyped by using npm install @type/library name. But what happens if that type doesn't exist and we get a 404 error? So let me show you a real world example. Let's take example of a tiny library called isOdd that just checks if a number is odd. That's simple. Here's the npm page for this library, just one function in it is odd. Very convenient for demo purposes, right? So as step one, let's go ahead and install it. So let's go to Visual Studio Code. Npm install is odd. Right, it's installed. So let's first get familiar with the type of issue that you are going to see. So to do that, let's create a new file and try to use this library. So I'm going to call it import.jslib.ts. I'll go to their npm page, copy the usage example, and paste. Now I'm getting a red squiggly under require, and it says require call may be converted to an import. So the issue is that TypeScript is suggesting converting the require call to an import statement. as require is typically used in common JS modules, which is library being an old JavaScript library is, while ES modules or ECMAScript modules, which are a new standard of JavaScript, use import for better type checking and module resolution. TypeScript would always push you to use the import syntax. You can get around this problem by enabling ES module interop and allow synthetic default import settings in tsconfig, but I don't want to get into that detail, so I'll simply accept that suggestion and change this const to import, and that error goes away, or rather shifts to the right. So what's happening now? Now we get the real problem. Cannot find a declaration file for module is_odd. Now TypeScript is complaining it doesn't have type information for that library. It is suggesting to first being to check if a type from DefinitelyTyped is available under @typescope, which should be step one, but we'll skip that since it doesn't align well with our demo, right? The second suggestion is to create a type declaration file with .d.ts extension containing declare module is_odd. That's what we are going to do. But you should always try the step one first. Before jumping to the type declaration step, we first need to inspect the code we are creating type definition for. Otherwise, there's no point. So to do that, let's go to node modules, is_odd, and in package.json, let's find a main section, which is here, which points us to the entry point of that library, which is index.js. Let's open this and inspect this. All right, so here's the is_odd function, and let's try to infer as much information as we can. So we can straight away see a couple of things. First of all, it is using module.export to export a function, which is the is_odd one. The second is that the is_odd function is taking a single value, which is being used in maths.abs. Now, maths.abs in JavaScript can work with both numbers and numbers as strings, right? So numbers in double quotes, they are valid inputs to maths.abs. So this value is definitely a number, but from the NPM page and the usage examples provided there, we can clearly see it's taking strings as well. So the value is of type string or number. That's the second information that we know. Now let's focus to the return type. This expression is gonna evaluate to a true or false. So we can safely assume that it returns a Boolean. Note that steps we just performed were necessary and would always be required to infer the type from given code. I'm trying to walk you through the process you would need to follow, and it would always be more complex than that tiny example in most cases. Now we need to decide where to create the declaration file. Easiest option is to create it in the source folder. A better option is to create a dedicated folder for types. So let's do that. So in global scope, let's create a folder called types. And in here, I'm going to create a file. And the convention is to use library name d.ts. So I'm going to say is d.ts. You can also have a global.d.ts file, which would be a single file for all libraries for which you want to declare types, but this is a better way. All right, in here, we need to create declare module is odd, just as it's suggested in the error message. Next, I need to add a line export equal to is odd. In TypeScript, the export equal to syntax in .d.ts file is used to define modules that export a single entity using module.exports in common JS libraries, ensuring that module's export structure is correctly understood by TypeScript. This declaration enables proper type checking and allows for correct importing in TypeScript code. This line is essential if module.export is being used, which is the case here. Okay, our type definition file is ready. Next, TypeScript needs to take this folder into consideration during compilation. So we need to inform TypeScript about it, otherwise it would be ignored. Now, again, two ways to do it. The easier one being to go to tsconfig.json and add the types folder beside this source folder in include property. The other way is to use the type roots setting, which is the appropriate location. So let's use that. Let's see if it exists. Here it is. commented out. So uncomment that and let me fill it in and explain the rest. Here we go. Note you need to specify both your path and the node module slash @types here as well. This is super important point if using type roots. If you don't use this setting in tsconfig, TypeScript automatically checks @types folder under node modules by default if that property does not exist in tsconfig, which was the case a second ago. But if you use it, only its contents are checked for types. Only. So you can easily shoot yourself in the foot by forgetting to include node modules, and TypeScript would stop looking for types from the DefinitelyTypes project. So use it carefully. All right, we can see redness of our file is gone. So I can go File, Save All to save all our changes. No errors here, which is good. So let's try it out. And we are getting true, which is the result for is_1. So let's confirm if that was indeed the case. And for 2, we get false. So everything is working. TypeScript is happy. We are happy. The world is a better place. But is it? Now that you understand how to get TypeScript working with JavaScript libraries, allow me to bring something nasty to your attention. So by now we have created a bunch of TypeScript files that get compiled to the dist folder as JavaScript files. But if we were creating a library to publish to NPM, can they be consumed by another TypeScript developer like yourself? And sadly, the answer is no, not in this state. You see, they are only JavaScript files. But you thought this entire curse of type definitions was brought about by those pesky JavaScript developers, and TypeScript developers were the good guys descending from heaven to fight evil. How can we contribute to evil the same way as they do? Well, that's where the free will comes into play. You see, the target audience of a TypeScript project is generally Node.js or browser, which are only concerned with JavaScript. So in most cases, creating those type definition files is a waste of resources, including computation and storage. So the option is disabled by default for good reason. The solution, however, is simple. You just need to turn an option called declaration in tsconfig to true. Here it is, which generates .d.ts files from TypeScript and JavaScript files in your project. Super easy, right? By default, these files would go to the same folder as JavaScript, but you can separate them out using declaration dir property in tsconfig. I hope by now you are fully familiar and functional with type definitions and can play around with these with confidence. And this concludes our practical TypeScript topic section. Lastly, we are going to go over some best practices for using TypeScript. So see you in the next section. Okay, our final section of this course is TypeScript best practices. Let's begin with one of the most important aspects of writing TypeScript code, the strict mode in tsconfig. Strict mode is a set of TypeScript compiler options that help catch potential issues in your code before runtime. By enabling strict mode, you are ensuring that TypeScript applies rigorous checks to make your code safer and less error prone. There are three key options we should focus on in strict mode: strict, no implicit any, and strict null checks. Strict enables all the strict type checking options in one go. It includes the other two settings, so when you enable strict, you get no implicit any and strict null checks automatically. No implicit any makes sure that every variable in your code has an explicitly defined type. If TypeScript can't infer a type for a variable, it will give you an error instead of just assuming any type. This is really important because any defeats the purpose of using TypeScript's type safety. Strict null checks ensures that null and undefined are not automatically assignable to any other type. This prevents errors where values can unexpectedly be null or undefined, making your code more predictable and reliable. When strict is enabled, you ensure that the code you write is as safe and error-free as possible. So when you are working on a TypeScript project, always remember to enable strict mode to get the most out of TypeScript static type checking. Next, let's talk about avoiding the any type. One of the most tempting things for a beginner is to use the any type. After all, it seems like a quick solution for types that are hard to define and also the quickest way to fix stubborn errors. However, using this type essentially turns off TypeScript's type checking, which defeats the purpose of using TypeScript in the first place.
Instead of any, we can use unknown, which is a safer alternative. When you use unknown, TypeScript forces you to check the type before performing operations on it, ensuring that you handle unexpected values properly. By using unknown, we gain the benefit of type safety while still allowing flexibility. So always avoid using any unless absolutely necessary and use unknown as a safer alternative. Next, let's talk about tooling. One of the key tools for any TypeScript project is the use of linters and formatters. These tools help ensure that your code is consistent and adhere to the best practices, which can save you a lot of time in the long run by catching errors early and maintaining clean code. Let's begin with ESLint. ESLint is a linter that helps you find and fix problems in your JavaScript and TypeScript code. It can enforce coding conventions, catch bugs, and ensure your code stays readable and consistent. To use ESLint with TypeScript, you'll need to install the necessary packages using this command. Once you have these installed, you can set up ESLint by following the documentation on their homepage. This configuration ensures that ESLint uses the TypeScript parser and applies TypeScript-specific linting rules, helping you catch common errors before they become a problem. Another helpful tool is Prettier from Prettier.io. Prettier is a code formatter that ensures your code is consistently formatted. It works great alongside ESLint to ensure both code quality and style consistency. You can install Prettier with TypeScript support by following their documentation. If you can't figure out how, let me know in comments and I'll provide you with solution or link to the appropriate video. And that's a wrap. You have just completed a crash course on TypeScript. We covered a ton from basic types and functions to generics, conditional types, and even working with third-party libraries. Whether you're converting a JavaScript project or starting a new one with TypeScript, you now have the foundation to write safer, more predictable code. Of course, there's still a lot more to explore in the TypeScript world. Yes, there really is, like decorators, advanced type manipulation, and configuration for large scale projects. But those can come later once you are comfortable with the core concepts. I really hope this course helped demystify TypeScript and made you feel more confident using it. If you enjoyed this crash course, don't forget to like, comment, and share it with someone who's learning TypeScript too. And if you have questions or want a deep dive on any topic we touched on, just drop a comment and I'll do my best to respond or even turn it into a follow up video. Thank you so much for watching and happy coding.